In this video, we will discuss the concept of consumer surplus, an essential concept in policy analysis. Let me first provide some motivation for the need of such a concept like the consumer surplus. Frequently, policy decisions is a binary decision of yes or no. Whether to implement a policy depends on the trade-offs between different pros and cons. For example, providing universal health care provides better health for the residents, which increases utility, but it requires a lot of financial resources. As another example, allowing Uber or Airbnb to operate creates more services in the city, which provides higher utility for the consumers, but it also hurts the local taxi industry or hotel industry and their employees. Part of the issue is that when we make these trade-offs, they would involve comparing utility levels to money. But how can we make a fair comparison between these apples and oranges? As a result, we need some concept that is a measure of well-being that is somewhat equivalent to money. And utility simply doesn't do the job. The concept we need is consumer welfare, and our familiar friend of the consumer surplus is a particular measure for consumer welfare. The idea of consumer surplus can be related to a mentality of savings from consumption. Let's say that we're willing to pay for a pair of designer jeans for up to $200, but you got it for $120 at a sale. So part of you might think, wow, I saved $80. Therefore, in some ways, we can think of this as your surplus from this consumption. The size of the surplus is just the difference between the most you're willing to pay for the item, which is $200 in the example, and what you actually pay, which is $120. Consumer surplus can be viewed as an extension to this idea, applied to the demand curve. One way to interpret the demand curve is to think of the price at each quantity as the willingness to pay for that particular unit of good. For instance, the consumer is willing to pay for a very high price for the first unit and a slightly lower price for the second unit, and so on and so forth. As the quantity increases, the willingness to pay starts to decrease. We can think of a consumer's quantity decision as comparing their own willingness to pay against the flat price that the seller charges for each and every unit of the good. If the price is below the willingness to pay for the first unit, then the consumer will decide to buy the first unit, and then think about whether they want to buy the second unit. And if the price is below the willingness to pay for the second unit, the consumer buys the second unit, and then think about whether they want to buy the third unit, and so on and so forth, until the willingness to pay dips below the price that is being charged by the seller. So for that last unit of good that the consumer decides to buy, the willingness to pay should be roughly equal to the price. And this is why on this graph, it says that the marginal willingness to pay for the last unit of output is actually exactly at the level of the price that's being charged. Taking this view, the consumer gains a lot of surplus from the first unit of this good, because their willingness to pay is much higher than the price they actually pay. As we slide down the demand curve, the surplus for each unit of good becomes lower and lower, until it becomes zero at the marginal unit of product, where the consumer stops purchasing. So to calculate the consumer surplus, we just add up all of these surplus unit by unit for this consumer. And the surplus for each unit can be seen as a small rectangle with a very, very thin base. Because the quantities are very, very dense, the bases are very small. So adding up all of these rectangles is equivalent to calculating the area of this wedge below the demand curve and above the price. From quantity 0, all the way up to the quantity where the consumer stops buying, which is Q1. And this is exactly the blue area marked on the graph. This is the idea of how to calculate the consumer surplus, and you must be familiar with this idea from the principles class. And next, I'll provide more details about the specifics of calculations. First, let me remind you about the concept of inverse demand curve, which will be very useful in a little bit. In the beginning of this course, when we plotted the demand function, which is quantity as a function of price, we understood that the plotted graph is actually the inverse demand function, which is price as a function of quantity, as opposed to quantity as a function of price. Now let's denote the inverse demand function by this notation with a superscript of -1 on top of D, so that we can understand that it is different from a demand function, which is actually a quantity as a function of price. These two different notations are very useful to help describe the way we calculate the consumer surplus in a second. All right, here's our key result here about how to calculate consumer surplus. And this is the first time we've seen integral in this course. But don't freak out. Let's unpack this expression slowly. From calculus, we know that integral helps us calculate the area below a curve. And this is exactly what we need. From the idea we discussed in the previous slide, we know we want to calculate the size of this blue area. And we know that the demand curve is the inverse demand function. So the entire area below the demand curve, between q equal to 0 up to q equal to q1, is just the integral of the inverse demand function from 0 up to q1 with respect to q. But then that would include this entire area from the horizontal axis all the way up to the demand curve itself. So the integral actually measures the entire blue area plus the orange rectangle. So to get the blue area we want, we just subtract the area of this orange rectangle. But here, the width is q1 and the height is p1. So the size is just p1 times q1, which is exactly the expenditure the consumer spends on good one. In other words, the size of this blue area underneath the demand curve, but above the price of P1, is effectively the integral of the inverse demand function subtracted by the expenditure of good one that the consumer spends. And this is the first way we can calculate the consumer surplus. This way of calculation is intuitive, but somewhat cumbersome. We can use a simpler and more direct way to calculate the blue area directly from the demand function, as opposed to the inverse demand function. So how are we going to do that? Recall that a demand function is quantity as a function of price. So if we integrate the demand function with respect to its argument, which is price, not quantity, then we're effectively adding up very thin layers of rectangles that are stacked up vertically like this. Once we see it this way, the area is simply the integral of the demand function on the p dimension from P1 all the way up to infinity. And this is exactly the definition of consumer surplus that is calculated by our second expression here. And these two expressions are completely equivalent to each other. For those of you who are interested in the actual derivations to show mathematically these two expressions are equivalent, you can look at this slide, and I'm happy to discuss the details with you. What we're usually concerned with when it comes to consumer surplus is how the consumer surplus changes, as opposed to its total value. For instance, if the market price of a good increases from P1 to P2, then the consumer surplus becomes smaller. What we're interested in is to measure the change or loss in the consumer surplus as a result of the increasing price. To calculate the change in consumer surplus, which we denote here by delta CS, we can calculate the consumer surplus after the change, which is the integral of the demand function from the new price of P2, which is higher, all the way up to infinity. So that is this expression here. And we can compare it to the consumer surplus before the increasing price, where the price was at the lower level of P1. And the consumer surplus before the change would be the integral of, again, the demand function on the P dimension that goes from P1 all the way up to infinity. If you're familiar with integrals, you will find this expression here, where the difference is simply the integral from P2 to P1 for the demand function. Graphically, this is easy to see. Before the change, the consumer surplus is this entire area above P1. After the price increase, the consumer surplus becomes smaller. And the change in the consumer surplus is effectively the integral of the demand function along the P dimension from P2 comparing to P1. But now you notice that what happens is that the lower bound of the integral is actually higher than the upper bound of the integral. So this value is going to come out to be negative. This implies the consumer surplus is actually decreasing. And the absolute value of the integral will be the same regardless of whether you integrate from P1 to P2 or P2 to P1. If you're not very familiar with the integrals, just know that calculating the integral between these two prices is sufficient. You can always reason out the sign of the change by thinking through the graph and economic intuition. If the price increases, the consumer surplus becomes smaller. We will look at a very specific example to see how this calculation works out. As a shorthand, we can remember that we will integrate the demand function from the new price up to the old price. Even if you don't remember the order of the limits, just remember to double check the sign against your intuition. Now let's look at an example. Let's say we have a demand function which is given by 12 divided by P. Then what is the loss in consumer surplus if the price increase from P1, which is 50 cents, to P2, which is $1? All right. Now, using the expression we just stated on the previous slide, we can calculate the change in consumer surplus as integral of the demand function from the new price after the change, which is P2, up to the price before the change, which was P1. Now we just substitute in the values of P2 and P1 when the price raised from 50 cents to $1. And the expression of the demand function in this particular example is just 12 over P. So we're effectively integrating this function of 12 over P with respect to P from 1 to 0.5. So to integrate this function, we understand that 12 is just a constant which comes out of the integral as a coefficient. So we're effectively just integrating the function of 1 over P with respect to P. And if you remember the rules of integral, the integral of 1 over x with respect to x is log of x. And you can always double check this by taking a derivative of the resulting function to see if you can actually recover the function inside. And we can verify that the derivative of log of p with respect to p will give you 1 over p. So the integral must have been correct. Now what's left to do is to evaluate the function we found at these bounds. So we're going to evaluate it at the upper bound and then subtract it by the function evaluated at the lower bound. So then that, use some calculators, you'll be able to find out that the value is approximately minus 8.28. So why is the sign of this integral negative? Well, that's not surprising at all. Because the price increased, the consumer surplus must have decreased. And we can see on the graph that the new consumer surplus, which is the smaller wedge, is smaller than the consumer surplus before the increasing price. Therefore, the change in consumer surplus is negative. In particular, the interpretation here is that as price increases from 50 cents to $1, the consumer surplus decreased by $8.20. In this video, we discussed the concept of consumer surplus and how it can be calculated directly from the demand function. This is a very useful tool in economics and policy analysis, and we will see many applications of this concept in class discussions.